Alright, chemistry class, let's talk about the changing model of the atom. So, it all began back in ancient Greece, around 450 BC. There's a Greek philosopher, Democritus, and he came up with the idea of atoms. He actually named them atomos, which is where we get the English word atom. And his idea was that these atoms were tiny indivisible particles, and so just like ball bearings or something along those lines. He didn't have any idea about protons, neutrons, and electrons, and atoms of an element could not be subdivided. So once you got to the atom level, you were as small as you could possibly get. Unfortunately, he wasn't all that well accepted because of the fact that he couldn't explain how these atoms stuck together. Aristotle and some other Greek philosophers argued, well, if everything's made up of these tiny indivisible atoms, then why don't they fall apart like a sandcastle does when it dries out and the pieces all just kind of fall apart. So really his ideas kind of faded away for quite a while. In the early to late 1700s, the whole century really, so there were two discoveries that helped revive that idea of atoms. So we've already talked last chapter about Lavoisier and his law of conservation of mass, and we've talked earlier about Joseph Louis Proust's law of constant composition. So remember, the law of constant composition says that a given compound always contains the same number of elements in the same proportion by mass. The example we used was water. So that led an English school teacher, John Dalton, to come up with the atomic theory of matter. He had 4 parts. So number 1, each element is composed of extremely small particles called atoms. Basically took that from Democritus. And all atoms of a given element are identical, but they differ from those of any other element. That's really the only original part. Number 3, atoms are neither created nor destroyed in any chemical reaction. Basically a restatement of the law of conservation of mass. And number 4, a given compound always has the same relative numbers and kinds of atoms. A law of constant composition, restated there. So again, Dalton thought of atoms as tiny indivisible particles, much the same as ball bearings or marbles, same as Democritus. So it wasn't really that much of an improvement, but it was bringing up the idea of atoms again, at least in European thought. While we're here talking about Dalton's atomic theory, I'd like to just give you the changes. So first one's okay. Second one, we should change to all atoms of a given element have the same number of protons. Okay, so carbon always has 6 protons. Nitrogen always has 7. And if you change the number of protons, you change the element. However, atoms of an element may differ in the number of neutrons. If you change the number of neutrons, you make isotopes. And if you change the number of electrons, you make ions. And we'll talk more about that in another video. The third one, atoms are neither created nor destroyed in any chemical reaction. It's true, however, they can be changed and actually created in nuclear reactions. So a lot of the last elements to be discovered are actually being made by nuclear reactions in labs, and they don't last very long, but we're making new elements, which is kind of exciting. Fourth part of Dalton's atomic theory is perfectly fine. It's just the law of constant composition again. Okay, after Dalton, we learned some lessons from static electricity. The word electricity actually comes from the Greek word electron, which means amber. It's actually spelled with a K. I forgot to go back and change that, auto-corrected to electron the way we spell it. So forever we've known that unlike charges attract, positive and negative, and like charges repel. However, it wasn't until Benjamin Franklin, the guy that founded our country, flew the kite with the key on it. Actually, story goes he actually got his son to do that. He was the first one to give names to positive and negative charges. So they could have been called anything, really, but Franklin was the first to name them, and he gave them the names positive and negative. So positive charges repel other positive charges and attract negative charges. He also discovered that lightning was basically a static electric discharge. So when the clouds are moving up through the atmosphere, they create a lot of static electricity, just similar to you brushing your feet against the carpet and the floor. And then that static electricity has to discharge, and it does so in a nice big flash of light that we call lightning. We also learned about cathode ray tubes. So cathode ray tubes are basically a evacuated air or a vacuum chamber that has an electric current running through it. The electricity is going from the negative side to the positive side. And if you put a special material in the cathode ray tube, you can actually see the flow of what we now know are electrons. They didn't know what they were at the time. And so the rays, which were these basically beams of electrons that are traveling across the evacuated or the vacuum chamber, and they figured out that they could spin a paddle wheel. So this is a little paddle wheel here. So they had mass, which was interacting and causing a change in momentum of the paddle wheel, and they were deflected by a magnet, much the same way that a negative particle was deflected. So we knew again from Franklin that negative and positive particles existed, and negative particles behaved a certain way. So there are these small things with mass that were negative that were traveling across, and so that's basically how we discovered electrons. There's a little bit more we'll talk about later. So now we know that there's positive and negative charges. A new model had to be describing the atom. So we came up with the plum pudding model, or in my opinion, the chocolate chip cookie model. So the plum pudding model had a positive mass of the atom with little negative charges stuck in it. Plum pudding is actually something kind of like a fruitcake, and I don't think any of you have actually tried it, but chocolate chip cookies are basically the same thing. So if you thought of the cookie dough as the positive charge and then the chocolate chips as little negative electrons stuck in it, that's basically the plum pudding model. Okay, it's one solid piece though. That was the model for a while. Then Rutherford came along and performed this alpha scattering experiment. So basically what he did, took a alpha particle emitter and shot alpha particles at a piece of gold foil. Alpha particles are basically helium atoms without the electrons, if you were curious. So he expected, just like if you shoot a BB gun at a tin can, that most of the BBs or most of the alpha particles would be deflected. However, when he actually did this, found out that 99% of the atoms or the alpha particles just went straight through. Okay, so it's like you're shooting at something, but it's not actually not affecting your bullets. It's kind of weird. So that led Rutherford to the idea that most of the atom is actually empty space. So over here is kind of what he thought was happening. The atoms of the gold are here lined up, just one layer thick. That's obviously going to be more than one layer, but when the alpha particles go through, if they go through the outside where the electrons are, they're not going to get deflected, like here. They're just going to go straight through. If they hit the side of the nucleus, then they're going to be deflected just a little bit. If they hit straight on, then they're going to be turned back. So this allowed Rutherford to explain what he was seeing in his alpha scattering experiment. So atoms are mostly empty space. In fact, like the vast majority of matter is actually nothing at all. It's just empty space. It's kind of weird. So that led us to the orbital model. This said that electrons are in fixed orbits around the nucleus, kind of like the planets going around the sun. And that was the theory for a long time. Neutrons were later discovered, and they were added to the nucleus because that's where we knew they were. Not much of a change, so instead of just protons in the nucleus, now we had protons and neutrons in the nucleus, electrons, again, in fixed orbits at first. Then came Heisenberg's uncertainty principle. Yeah, same Heisenberg that old Walter White named himself after, a little drug pseudonym. So Heisenberg did some experiments that prove that we can actually never know the location and speed of an electron at the same instant. They actually have a lot of freedom. They can change where they are and what they're doing based on the amount of energy available to them and a few other things. This led us to the idea that electrons aren't in set paths like the planets around the sun, but have quite a bit of freedom and can move closer or further away from the nucleus. That has led to our current model of the atom, which is the electron cloud. Okay, so still we have the nucleus with protons and neutrons in the center, and then around that is the cloud region. So this is where the electrons are likely to be found. They can be outside of the cloud. They're not stuck inside of there. It's not like a border. But the majority of the time, you're going to find the electrons in that area. We don't know for sure where, but they're in there. This diagram over here on the right is actually a model of one of the first orbits, or the electron clouds. So you see the nucleus here, and then these are actually where the electrons were at any given point. You can see they're kind of clustered in a circle around, but there's some that are really far out there, like this guy here, this guy, and some that are really close to the nucleus. So again, electrons aren't on set paths. They have some freedom. They're allowed to move closer to or further away from the nucleus based on how much energy they have at the time. So that's the current model of the atom. If you have any questions, talk to me. Otherwise, you're good to go.